All right, so I am Mary Thomas, and I want to welcome you all to the fourth annual HPC User Training Series. We're pretty excited about the program this year. We've made some changes, and it's reflected in the very large number of people who have joined and registered for this event. So it is taking a while to admit the group, and Cindy and Susan will be working on that in the background. So you may see lots of little admit signs, but I don't have to worry about them. So the program is interdisciplinary. We've been doing it for a while. It started out of a need to train undergraduates in parallel computing for a competition, and it's grown, and we're really happy with how it's grown. So first of all, welcome. We'll be meeting every Friday for several weeks during the winter quarter, and then again, we'll have 2 sessions, and the second session will be in the spring quarter, and lots of activities associated with this. You'll be given the opportunity to have an account on EXPANSE and use it to run some basic training exercises. We're working on that, and we'll work with you on that. But first, I want to give you an overview of our motivation and why we're doing this program. So there's the title of this is HPC and Cyber Infrastructure Training, but what does that mean? And I'll get into the way we refactored the training program so that we can introduce people who we think of as non-programmers, people who may do some programming a little bit, but they're not parallel computing programmers, they're not developing advanced applications, but they need to run jobs on our large supercomputers and also cyber infrastructure. So I thought I'd have a little fun time showing you a very high level view of what do we mean by cyber infrastructure from the perspective of parallel computing, high performance computing, and what do we mean by high performance computing. And the terms are cyber infrastructure. It's used to connect a large number of resources with distributed and emerging technologies. You actually use it every day. You just might not be aware of it. And it includes high performance computing, where we aggregate and integrate a lot of computing power so that millions of computers can interact with each other at one time, basically, and large advanced networking to move a lot of data. And then these large data sets, if you're involved in scientific computing at all, you know about big data. Terascale used to be the big number, and now peta, exa, zetascale numbers are common out there in distributed computing. And so the overall goal when you combine high performance computing and using cyber infrastructure is to deliver higher than usual performance, which is now becoming ubiquitous. Back when I started, high performance computing was just a small elite group of people doing astronomy calculations or advanced molecular chemistry. We still have those people, but now everybody has a lot of advanced computing requirements. But they are intended, high performance computing, to solve very, very, very large problems in science, engineering, business, social media, a lot of applications. So you use it every day. HPCCI, it's everywhere. So this just shows a little cartoon that I took from the Washington Post talking about security, but it kind of gives you an idea of the complexity of the flow when you just go to log on to a web browser, or here somebody is trying to just log into a system. You're on your local device, which is usually a laptop. It could be your mobile phone. It could be a local workstation. You send some signal through your local network, and out on the network, a decision gets made to route your request somewhere through some servers, and they're eventually to get down here where you want to do your work. Maybe that's just running a Google search. You need to get somewhere. The servers will figure out an optimal path for your data to move through the system, and may go through several servers. You can see in this little cartoon. Eventually, you'll end up on the Acme web server doing your work. And that Acme could be, like I said, Google. It could be running jobs on a supercomputer. There's a lot of variety in what you're trying to get done. But that's what we now think of as cyber infrastructure. I'll show you some numbers that, well, here they are. This is called the internet, right? It's an aggregation of a lot of devices, hardware, software, and messages that travel around. And the internet reaches 65% of the world's population, according to this Washington Post article, 5.6 billion people. 93% of the people access it using their mobile phones. And the data consumed globally in 2021 is approximately 79 zettabytes. That's a zettabyte is 10 to the 21 bytes, and they expect that to go to 180 zettabytes. So the world you live in now is high performance computing, and it needs cyber infrastructure. How do you move all those messages around? So I want you to be aware that what you're going to learn in this course will also inform you on how things are working for you. So just some other information. The number of people using social media platforms is in the billions. And this is just a cartoon diagram. And this is shows you, the other high level, often used websites that are out there on the internet. And then this all in 1 minute, this gives you an idea of how much work is being done. And this is big scale computing. And the universe of the internet is facing this need, this challenge to store the data, process the messages, and then provide quick and easy access to the users. That's you. So that takes, you have to put the data somewhere. It has to move on this fast network, but you have to put it somewhere. And an innovative idea that's evolving right now is to put everything where it's cheap and easy to keep cool, because storing, as you know, all this data and running these applications, it requires a lot of power. Power usually translates to heat. How often does your laptop overheat, or your mobile phone if you're doing a lot of work on it? And so when you're trying to stage and store zettabytes of data, we don't want to lose that data. You have to have it be cheap and cool. So they're now, Iceland has been promoting itself as a place to store data. And they're building fast, high-speed networks in and out of Iceland. And there's this evolving idea that's been proposed, which is basically to build a tall skyscraper of data storage facilities. If you look at the scale here and you investigate this a little bit further, these people are actually going to walk in, and this is like a lobby with elevators going up to the storage devices. So they're going to go vertical. Of course, with global warming, even Iceland is challenged now. So there's all these challenges that are being taken care of for you when you do fun things. So the other thing is, how do we send all this data? We have to have high-speed networks. It used to be a megabit was pretty exciting. Just getting 100 megabits to your house, even now, is still expensive. We, in the high-performance computing CI world, the high-end scientific applications that you'll be learning about and techniques, we need gigabit networks in order to connect all the resources that are distributed around the world. And the world is now connected with faster and faster networks. And what used to be in the domain of supercomputing, high performance computing, high-end applications is now needed just to serve the billions of people trying to move those zettabytes of data packets around. And every global location is just as important as the other. So there's all these activities out there to interconnect the world. And it all is generated from the highest end supercomputing, which is what we do at SDSC and in our network of resources. This map also shows you a large number of places in the United States and the networks connected between them that are 100 gig. So the fun thing about supercomputing and high performance computing is we're always at the cutting edge of these technologies. It's great fun. So I like to show this fun map or idea of what a supercomputer is. And back when supercomputers, multi-nodes, multi-device systems were being built, as a joke at Oak Ridge National Lab, they built what they call the stone supercomputer, and it comes from this story of a village where there's no food, and somebody puts out a pot of water and puts a rock in it, and people walk by and they say, "What's that rock doing in that bowl of water?" "Well, I'm trying to make some soup, but I don't have much to put in it." And the village people go, "Well, I have a potato," and somebody else says, "Well, I have a carrot." So they start dumping food into this pot, and they make a village soup. And the idea here is that the scientists at Oak Ridge went around all of Oak Ridge National Lab, gathered up all the old desktop workstations they could find and put it together. And they actually claimed to make the cheapest cost per flop. They had a 20 megaflop computer, but this is kind of how supercomputers used to look. And now they've evolved a bit to something like our advanced EXPANSE, which is a more advanced, higher end. So what we have now are systems like EXPANSE, where not only do we have high performance computing racks in a data center like at SDSC, where there's thousands of compute nodes and compute GPUs, CPUs. These are all locally located close together as a cluster, but also it's connected and designed to have remote cyber infrastructure connectivity. And again, cyber infrastructure is big data, it's message passing, it's going out and using devices like we have the Wi-Fi project, which connects to fire sensing instruments that are located in Southern California. EXPANSE is a special kind of machine. It's developed to target what we call the long tail of science. It's people who are doing very important computations, but they have modest scale node requirements. And so just a few thousand cores would make them happy. And in the next few weeks, all these terminologies will be explained in more detail. So I'm not trying to brush by them. I just want to give you sort of this overview that these systems are big. We call each one of these a compute rack or a scalable compute unit. On each one of these racks, we have a CPU and GPU and data all in one little small location, so you can more efficiently move data around. That's different than moving your petabytes of data to an isolated storage system. That would require different technologies. We can connect to them through this CI integration design that's built into EXPANSE. But the idea is that there are applications out there that need to run on a million cores, and they belong on a different kind of system and a different kind of architecture. Imagine coordinating the computational effort of a million cores. That takes a real specific kind of software perspective and technologies. For thousands of cores, it requires yet another kind of technology, and that's what we focus on here at SDSC, is we're looking at this long tail. It turns out the long tail comes from the fact that if you look at the size of scale of HPC applications, typically there's a few of them that need 1 million, but most of them in general need these modest scale. A few thousand cores is what we now call modest. And so systems like EXPANSE are dedicated to that. We're based on the AMD EPYC processor for CPU compute, and we use NVIDIA GPUs. We have V100s and we're adding A100s. So we'll always be upgrading EXPANSE. It's a 5 to 10 year system. Okay, so again, we have large scale local petabyte performance, high performance storage. It's a great system, and you guys will get to work on this as part of being in the course. Again, to move the data, we need high-speed networks. And this is a somewhat older version, 2017, I think, view of the EXCEED interconnection network and the systems that are on EXCEED. EXCEED is funded by the National Science Foundation, and EXCEED stands for Extreme Science and Engineering Discovery Environment. It's been going on for over 10 years, and it's going to be evolving to a new system in the next couple of years, but we're part of the group of high performance computing centers that provide resources, and that usually means HPC computers like EXPANSE, high storage capability, and then the ability to move data in between them with efficiency. But the rest of the country is benefiting. Like in California, we have the Scenic network, which is high speed as well, and it interconnects, and it's 100 gigabyte. And so the technology typically developed for these high-end systems from like the NSF funded ecosystem, it bubbles out to eventually to commercial applications. But we also try hard to use commercial technologies. By the way, if you have questions, feel free to use the chat. With so many people, as you can see, there's a large participation. We have, we'll look at questions and answer them all. And generally there'll be staff available and participating that can answer your questions. So feel free to put a question in there. We'll get to it. We'll make sure every question is answered directly or in the chat. Okay, so that's sort of an overview of, what's high performance computing and what's cyber infrastructure. It's not a huge mystery, but it has its challenges on running an application. Let's say you've run TensorFlow on your laptop and you're doing some machine learning calculation, or you're running MATLAB on your laptop and you're doing some other kind of molecular dynamics. And all of a sudden you're doing more data and you're making more data, and your laptop takes longer and longer to do the computation. And then you go to a workstation at your university, and then things run faster because the workstation's maybe bigger. And then eventually you go to a small cluster at your university. And then eventually your problem is so big, it needs so much memory, and it puts out so much data that you have to come to a really big system. And obviously, when people come to work on a system like EXPANSE, we try to make it as easy and straightforward as possible. And we feel that by getting some of the basic concepts across, that will make it easier for you. Knowing, though, that you're doing this every day, but somebody has already taken care of message passing for you and load balancing, a lot of that is nice to know that the systems we're presenting to you, they're not too mysterious, but they can be challenging, and we recognize that. So that's why we started the user training courses. A lot of the supercomputing centers present training. There's a tremendous amount of training out there. And so our training is focused on EXPANSE and the kind of problems that we can solve on EXPANSE. It's designed to promote what the NSF calls workforce development. We recognize that a lot of this stuff might be taught in undergraduate classes or not. Parallel computing is not taught as widely as we feel like it really should be. A lot of students are learning that they have to learn multi-core, multi-threaded processing to write some of the code that's needed to support the internet. It's parallel computing distributed all over the world. So we put a lot of effort into our training, which is the researchers and their graduate students who need to run high-end applications on a system like EXPANSE, or even bigger as their program grows. And it's free. It's funded by the NSF, so it's open to all valid users, including students at UCSD, postdocs, researchers, and collaborators of SDSC projects and systems, Exceed, for example. And to encourage more student participation, we have an HPC students program. I'll talk briefly about all of this. The scope, we refactored our training. This is our 4th year. And we realized, and this is a concept that Bob Sinkovitz came up with after observing, and many of the people in the user services group, that a lot of the users on EXPANSE, they're not programmers. They're using an application that's already designed. Games, Amber, some molecular dynamics applications. They come in, they want to run their data and run it using these already built applications. And EXPANSE is designed for that kind of environment. It's still challenging. You still have to know where your files are. A lot of people end up working on gateways where you use a web browser and a team of technologists get the gateway working for your application for what's maybe a community model. And we have the neurosciences gateway and other gateways for that. But you might be in the middle where you have an application. Your advisor said it's running on EXPANSE, go make it work with this new data set or this new idea. And so we wanted to refactor the training so that the first session is just parallel programming concepts. What does it mean What does it mean to be doing parallel programming? What are the concepts behind HPC systems, etc.? And then the second session would be for programmers, people down in there developing parallel code as opposed to using already made parallel code. That doesn't mean it's straightforward to use existing code, and we recognize that. We know that you need to understand what it is you're working on, the CPU and the GPU architectures, what the software is. You need to understand Linux, and you need a few admin skills. You need to understand what it means to run an HPC application. And in all these different areas, we understand that you guys will be running different kinds of applications. You may need to be familiar with cloud computing, visualization and analysis of big data, certainly. We want you to also then in session 2 learn the basics of parallel programming, MPI with C and Fortran, Python, and to do performance analysis of how well is your code running. And that often takes some experience and insight. And then in our training, we always try to include current trends, like now we're teaching machine learning, containers, Singularity, Kubernetes, Jupyter Notebooks, and cloud computing. So you've looked at this. This is the schedule that we've got, session 1 and session 2. I think most of you are signed up for both. So each week we'll have a different topic that we cover, a different presenter, or maybe part of our group. And what we try to do is for each of them, we try to have some kind of exercise or reading, some other training material that you can go and look at. We record all of the material and convert them to what we call an interactive video. So you can search through a presentation after the fact, look up terms and technology, terminology, and go through the presentation so that you might get a little more out of them. You'll have a copy of the presentation, the PDF file. And this is a pretty well set agenda. Of course, things always change when somebody might not be available, but we'll try to always give you a good warning on that. So the first session is ends on March 4th, right at the end of the spring quarter. Then we kick it back up for the winter quarter, then the spring quarter. These are synced to the UCSD quarter system. So we set a record for registration. I want to thank all of you. We had over 150 people have registered. A lot of them are graduate students, and we just really welcome all the students that have taken time to come to this, and hope that you can get a lot out of it. Like here's a little distribution of our participation. We've never had that many people register, so this will be interesting since a lot of this is virtual. We wanted to do in person this year, but with the Omicron virus and the way things are, we felt it was just smart to stay with virtual technologies. But we welcome all of you, and we'll do our best to be responsive to all of you. Although 150 have registered, we recognize that not get very active, and that's okay. We want you coming to the talks. We want you listening and learning. All right. There is a little bit of a count of some information out. There are 66 unique institutions. There wasn't room to print them all out, but our big participants are UCSD, Utah, UCSB, University of California, Santa Barbara, and Santa Cruz, and Berkeley, and San Diego State. We welcome all of you who have come from a site with multiple participants. This is a list of your mentors. There'll be a link to the mentors on the GitHub repository. I'll go over that in a little bit. So myself, Marty Candace, Andy Getz, Paul Rodriguez, Mahi Tautanini, Cindy Wong, Susan Rathburn, Bob Sinkovitz, and Jeffrey Weekly from University of UCSC, Santa Cruz. All right, so to get started, and at this point I'll take a pause in my presentation. You have to do a little bit of work to get started. So you have to register for the training, which you've done, and then you need to obtain an EXPANSE account. Some of you already have an EXPANSE account, and that's great. And to get one, you need to, if you don't have one or you don't have an Exceed account, you have to go to the Exceed portal and create an account there. And once you get that portal account created, you'll get a portal ID. Then you need to get that portal ID to me. And so you're going to use Google form here and give me that portal ID. Once I get the portal ID, I'll add it to you. I'll add you to the training allocation. And then it takes a little bit of time for the Exceed computer system to get you added, and then some notice comes out to our account manager people. Nicole and Marty are working on this to make the Exceed account. So it could take a few days, but within a week you should have your account on EXPANSE. So you'll get a notification, and make sure you can log on, and then you'll be set up to run jobs on EXPANSE. This whole process can take a few days. And so let us know if you're having any trouble. In this form where you enter the portal ID, you can also make a note, hey, I'm having some problems, and we'll get in touch with you. And you can also then go in and start cloning the GitHub repo. And if you don't know what GitHub is, we have some links that you can look at to learn about GitHub, hopefully by now. The homework for week 1 is this getting started and getting that EXPANSE account set up. So with that, are there any questions? I'll stop sharing for a moment. Anybody have any questions?
Mary, could you link the
GitHub repo?
form? The form.
Oh, the form, yeah.
I just put it in the chat for everybody.
Yeah. Oh, thank you. Thanks, Marty.
I'll throw the GitHub in there too for make it easy.
All right. Wow, it's just nice to see so many people showing up today. All right. So any other questions just about the overview or the process of the, let me show you the repository. Bring this down here. Nope. That's the simple form. It's a very, oh, I've already responded. So it's just a couple of things that we need. And I'm not sharing my desktop anyway. Let me go ahead and fix that. There we go. Can you see my web browser and my talk? All right, this is the training, a GitHub repository. And again, I haven't uploaded my talk yet, but you'll get some instructions with some tasks that might be in there. And we try to get the presenter talks up as quickly as possible to show you, so that you have access to the presentations. There's no due date on the weekly tasks, but it would be good, you'll have more progress and momentum if you do try and keep up with the work every week. You can do it whenever you want, though. The whole point is not to give you, there's no grade. If you're an undergraduate student, you can get a co-curricular record credit if you complete the work. And you can get in touch with me about that. Any other questions that I need to be looking at? I assume we've got people here to help with that. Okay, so you can get started, and next week we'll, getting back to the schedule, Bob Sinkovitz will start talking about basic parallel computing concepts to get you familiarized with that. Okay, so if there aren't any other questions, I want to talk about another program that we've got, which is the HPC Students Program. Oops, let me get this out of the way. All right, let me go into. Okay, you can see my presentation. Okay, so I welcome all of you who are students. It's great to have you around. One of our motivations for the first HPC user training was to teach undergraduate students about parallel computing, so we could do a popular activity called the Student Cluster Competition. And we were surprised at the number of students, but also the number of faculty, graduate students, staff from both SDSC and Southern California and all of the Exceed, the diversity and the broad response. It was really interesting. And today, with 150 registrants and 66 institutions, it is evidence that there's a lot of people who are out there who are interested in learning more about HPC. And so, we welcome you and we're looking forward to working with you guys. Typically, out of the 150, 100 of you will become active. And EXPANSE can handle that, and our program can handle that. We've got lots of mentors who are part of the training activity. Okay, so for students, we have, for mostly undergraduates, we sponsor internships that are paid and co-curricular record, which is a University of California program, which is really interesting. You have to write them and meet core competencies in educational aspects of and technology aspects of your project if it's technical. And the students will get an official record that comes with their transcript to say, for example, I took the HPC user training and I learned all these key HPC concepts, so they can use it when applying and interviewing for jobs. And the HPC training and other activities, you can, if you're an intern, SDSC has a research internship. For this HPC training, we also have research, the CCR for that. And internships can be paid or volunteer, I should have put that on here, or something that gets you they all can get you CCRs. We have the Supercomputing Club, which is led by the students. And we have a few projects. They hope this year to do a Raspberry Pi cluster build out. Unfortunately, we've had the budget. We haven't bought the hardware since 2019, but in 2020, our plan to build it got impacted by COVID. 2021, it got impacted by COVID. So we're hoping 2022, we can build out a Raspberry Pi cluster. So there are students already interested in working on that. And then they also want to do other activities like developing software for high-speed data file systems, working with the D3 Data Sciences Club. And also one of our big activities is supporting student participation at supercomputing. We've done the student cluster competition now. They're for supercomputing 21, supercomputing 22, we're already planning. And we've done student volunteers for this year, last year, and in SC19. In SC20, no one chose to go, and SC was all virtual. And so there's multiple ways that students can participate, and we try to find and help sponsor their travel if the meetings are held in person, and sponsor their activities to get them more involved in supercomputing. And all expenses are paid by SDSC and club sponsors if you get selected. For example, the student cluster competition activity is very competitive, and you have to work hard to get picked to be in the competition. So HPC students, you can get in touch with me if you have other questions. This year will be the students, the team last year, half of them were from our SC21 team, 20 team, and this year we have more coming back to the 22. So we're already starting to plan. And so if you're interested in student activities like that, hopefully it'll be in person in Dallas this year. So it's been around since 2007, and the goal was to start bringing in undergraduate and even high school students into supercomputing. It's clear that there's a lot of graduate students working in the field, but undergraduates, it's really important to start motivating. And some of the outcomes from this program are this program, the actual student cluster competition, which is ongoing. But the ACM and the IEEE both have high performance computing undergraduate education programs. IEEE is working on formalizing, they've been doing it for 10 years now. What competencies do students need to be parallel computing, HPC, to get a degree in that area? And also ACM has high performance computing chapter, and they both sponsor student chapters on campuses. We have those both at UCSD. As part of the supercomputing student cluster competition, the students learn in person to design and build and run their own cluster. Typically you work with vendors like Dell and Cray and HPE, Hewlett Packard, and other companies, ARM, and AMD, to build out a cluster. The students have to bring that cluster then to the competition. So they have to pack it up, ship it, get it running over the weekend, and start competing on Monday with the competition. Once the competition kicks off, they have 48 hours to run a suite of applications and keep the cluster running, usually within some strict power limitation. This year it's 3 kilowatts. And this one, they have different challenges. One is the reproducibility challenge, where they attempt to reproduce a scientific paper, which can lead to publications for the students. Our team last year did well enough that we got a publication out of that. So it's really good for developing students' backgrounds who are academically inclined. But also, if you really love working with high-end computing, you learn how to build and run a cluster and install the software. So we'll see what happens this year. The plan is it will be in Dallas. So the entering is competitive. You have to write a formal application. We do that with a team of mentors, a group of interested students and vendors, and they commit to loaning us hardware, and students commit to working with the hardware through the summer and the fall and traveling to supercomputing, and mentors commit to working with the students on either the hardware or these applications. And I'll talk about that in a moment. The team is a maximum of 6 undergraduate students, but what we do is last year for the first time, UCSD undergraduates got credit for an independent study course, and we allowed any student who was interested to participate. We ended up with about 15 total students who all got experience working with the competition and learning about the applications, and 6 of the students were part of the formal travel team. And if we had traveled, they would have gone, but what they did was they met for 48 hours in a large conference room at SDSC and competed, and they did very well. I'll talk about that in a moment. But the participation has some commitment, but it's an experience of a lifetime. The Thread Shredders, that was the name of our 2021 team. They finished 4th overall. Again, last year our team finished 4th overall. This year there were 10 teams around the world. The competition was virtual. The challenge was that it had to be on 2 kinds of cloud computing resources. So these are the 6 students: Kai Wen He, Aranav Gupta, Jihao Kong, Matthew Mikalo, John Gee, and John Lee. And Kai Wen, Aranav, and Matthew will be returning to work on the SC22 competition team. So we'll have this pipeline of experienced people working with newbies. It'll be fun. So the strategy to get ready for this takes a lot of work. First, you have to do like the HPC user training class or self-guided tutorials, or take, I think Ryan Kastner is teaching an introduction to C to parallel concepts as well. And again, he had over 140 students, I think, register for that as well. So you have to have some competency, and that makes it easier to learn everything you need. You have to participate in weekly meetings with the mentors and the team and develop some hands-on experience. We start with EXPANSE, and you run all these high-end applications. I'll talk about those in a moment. We have a lead and a co-lead for each of the applications, so everybody at the competition know how to do most of the applications. And if one lead gets sick, then we have somebody else who can take over. It's a backup system. And you have to learn to optimize the performance for these applications. It's actually more important to learn how the application is running than really what the application does. Although interesting, it's more important to make it run well. You have to learn to launch. This year, we had to learn to launch virtual machines on both Azure and the Oracle Cloud. So we had to learn about Azure technologies and Oracle Cloud Technologies. And then we have to develop tools for monitoring the virtual machines. This is a poster. You always have to make a poster for the competition that shows everything in a nutshell of what the students had to do. Some of the tools they learned to use include BGFS, which is a high-speed file system. CentOS is the operating system. SPAC is managing software installation. EPIC was the CPU that we used for our computing. And I should have on here also point out that we used NVIDIA V100s during the competition. There were A100s available, but they ran out because they're so popular. The A100 allocations were consumed by commercial, so we didn't have access to them. That was an interesting experience. We use InfiniBand, Chef for developing scripts to launch VMs, and Slurm, and other technologies. These are the applications. The top three are what we call the benchmarking applications: high performance LinPack, high performance conjugate gradient, and the IO 500. And then the high HPC applications this last year included Cardioid, Quantum Espresso, a Bayesian network application, and then a mystery application. Next year in SDSC 22, these three applications here and the mystery app, they'll be different. You can always count on the benchmarks. And in this table, the students had to do a cost analysis of how much it would cost to run the application on either the Microsoft Azure Cloud or the Oracle Cloud, which was interesting. It's different from having all these applications installed and running on bare metal, what they like running on EXPANSE, and how much power they might consume. But to the cloud, when you move to the cloud, you don't worry so much about power. The students had to worry about cost per flop, per competition points. So that was a different way of viewing the work. Some of the tools they developed as a job predictor worksheet, a job scheduler. When are you going to run these? And do you have enough VMs available? And at times they ran out of the A100 VMs during the competition. That was a learning curve. And also you can use, like the Azure people have a portal where you can monitor your machine. Is it up and running? And how long has it been running, et cetera. And then you also need to look at the costs of the cloud computing and how much cost per hour. These are some of the tools. And then the competition committee has a Grafana display portal. They call it the leaderboard, and it tells you the progress of the different teams and the different, like this is the benchmarking applications, and then down here is the reproducibility challenge, for example. It was a long leaderboard. This is only about a third of the leaderboard, but it gives you an idea. It was very exciting to watch people post and provide information. Accomplishments, SDSC 21 was all virtual. They learned to run things on Azure and Oracle, and we hope that SDSC 22 will be in person in Dallas, but if not, we'll be prepared to flip the switch and go virtual. The team last year did very, very well, and they improved some of the benchmarking of the SDSC 20 team. So in SDSC 22, we'll try to improve our benchmarking again, even more. So we have a lot of sponsors that support us financially with hardware, with software. I want to thank all of them: AMD, NVIDIA, Azure, Oracle, GitHub, Amazon Cloud Bank, NERSC, Oak Ridge National Laboratories, ARM, Hewlett-Packard, the Data Sciences Institute, and UCSD, SDSC, NSF, and Exceed all make this kind of activity possible. With that, I'm pretty much done. The next slide is tasks for week 1. So again, sorry, you can't read that all. It's clear on the GitHub repository, which I've stood up here, and we'll be adding the weeks and more information over time. So are there any questions that I need to worry about answering? With that, that's it. Thank you, everybody, for your time and attention. Really appreciate it. And I can answer any questions. Thank you for staying around. We look forward to working with all of you. It should be a lot of fun.